Okay, hi guys. So in this lecture we'll be continuing on the SN1 reaction, and we'll be seeing some of the examples wherein you need to compare the rate of SN1 reaction in the following compounds. Okay, so let us get started. So the question is compare rate of SN1. Okay. So we have this and this. Please remember please remember that in SN1 reaction there will be no nucleophile because the rate will not be dependent on the nucleophile. So directly we'll be putting the substrate into the polar protic solvent. Okay, so what would be the rate of nucleophile rate of SN1 reaction in this case? So more stable the carbocation, that is the rate determining step, that is the product of or intermediate in the reaction. So that is the product of the first step, which is the rate determining step. So more stable the carbocation, more will be the rate. Hence in this case 1, 2, 3. Okay, second question is between this and this. Okay, so what would be the rate? So as you can see that in this case the carbocation would be more stable because of the resonating structure from the phenyl. In this case there are 3 phenyls, in this case only 2, in this case only 1, hence the stability of the carbocation would be in this order, and hence the rate of SN1 as well. What about this? So what is the stability of carbocation in this case? So as you can see that the first compound on having carbocation at this carbon will be turning anti-aromatic. This compound will surely have resonating structure which is absent in this compound, hence 2 would be greater than 3 only because of this conjugate double bond which can have conjugation or resonance with the positive charge here. Rest, hence 2 would be more than 3, and they both would be more than 1. The rate would be more than 1. Why? Because of 1 has anti-aromatic characters. Okay, let us discuss about this. And we are, so as I have also mentioned that the rate of SN1 will also depend on the leaving group. Okay, so if you see the leaving group, Cl minus is the leaving group here, and Br minus is the leaving group here. So Br minus is more stable than Cl minus, as we have already discussed. Why? Because Br minus, the size of bromine atom is more than the size of chlorine atom, hence negative charge would be more stable in a bigger sized atom due to less electron repulsion. Okay, so 3 would be more stable than 2, would be more stable than 1. And why is the case that we have not discussed 1? We don't need to have even discuss 1 because it is the formation of highly unstable aryl cation, so we need not discuss it. Okay, we have this and this. Again 1 would be more stable than 2. Why? Because of the highly unstable vinyl cation formation in the RDS. Okay, let's discuss this between this and Br. So obviously, as you can imagine, the rate would be 2 greater than 3 greater than 1. Why? In this case, at least carbocation formation has a conjugation with a pi bond. In this case, no conjugation with the pi bond, and we need not discuss even about this compound. Why? Due to the formation of again vinyl carbocation, highly unstable. Let's discuss about this. this and this. Okay, so what would be the rate? 1 would be more stable than 2. Why? Because of the lone pairs. So the positive charge, if it comes on this, it can have a conjugating structure, whereas it can only have one conjugating structure. Okay, let's take the next example. We have this one and this one, and obviously simple cyclohexane ring with the iodine attached on it. Okay, so what would be the rate? Obviously 1:2:3. Why? Because we have lone pair of oxygen here. It will be getting involved in the resonance with the positive charge. It will be formed in this carbocation. Similarly on this we have only 2 resonating structures. It is extended resonance, and it is two-side resonance or separated resonance, or it is not having external resonance. Basically the thing is this, it is involving whole of the compound in the resonating structure, and it is not involving whole of the compound. Okay, and so with this we come to the next question, which is identification of major products. Identify major products in the reaction. Okay, so in identification of the major products we have something like this. On reacting with H2O will give something like this. Now how is this possible? If you look closely on this, the carbocation formation in the first step, or the RDS, would be something like this. Then I hope you remember about the 1,2-CH3 minus shift, because the number of alpha hydrogen here are only 3, and if you actually shift it, the number of alpha hydrogen will be, how many number of alpha hydrogen are here? 3, 3, 7 alpha hydrogen here, only 3 alpha hydrogen here. So this is going to be a forward direction CH3 minus shift. Hence the H2O molecule will attack on this carbocation, and we will have something like this as our final product. Same. Okay, now the next question is, you have to identify the major product. This was the first example. Now comes the second example, where we have this. So the major product formed in this case is this. And how? Because in the first step, or the redetermining step, we would have the carbocation something like this. Now again 1,2H minus shift happens, and it would be in the forward direction. Why? Because in this case the number of alpha hydrogen are 3, and if we draw the intermediate after the 1,2 minus shift, so in this case the number of alpha hydrogen would be 4 plus 3, 7 alpha hydrogen. 7 alpha hydrogen. Hence this would be in the forward direction. Therefore H2O would react on this to form a product like this one. Okay, so in the next example we have to show that which of the following compound will give same SN1 and SN2 product. So the question is, which of the following compound gives same SN1 and SN2 products. Okay, so the options are, we have this one, B is phenyl ring substituted with this group, C is this group, and D is this compound. Okay, so the correct answer would be D. Why? Because in this case the major product formed would be, from SN1 it would be something like this, and from SN2 it would be something like this. This is SN2, SN1, this is SN2. From this, the major product for SN1 would be, and for SN2 would be, okay. I hope you all are following this. This is for A, this is for B. Let me write down for C. So for C, the major product that would be forming would be this, and for this, major product forming would be this. Okay, this is SN1, this is SN2. For this case, I hope you guys take this for homework, and you should be coming up as to why I draw this compound and why it should be the output. And for this, there is no scope for 1 to minus CS shift or 1 to minus H minus shift. So the product for SN1 and the product for SN2 would be same in this case. This is T. So with this, let me write down a note at the end that if carbocation formed undergo rearrangement, then SN1 and SN2 products are different. So in all the ABC cases, there was some sort of rearrangement because of the resonating structures or CS3 minus or H minus shift, due to because in those cases carbocation could have been more stable had they been undergone a rearrangement. But in SN2 there is nothing such type of rearrangement possible. So if carbocation formed undergoes rearrangement, then SN1 and SN2 products are different. Okay, so with this we come to an end of this lecture. In the next lecture we will be seeing some more examples of stability of SN1 intermediate. So till then, good luck and good